So should I perhaps apologize to the audience that I have changed the title of my talk, but on Monday we were essentially in discussions already discussing the things I wanted to say in my talk, and I thought that it might be better to give a talk that would be of interest to a wider group of people rather than just being a specialist talk. And so here is a talk that is, the first half is a little bit of philosophy, I think that everybody can have an opinion on, and hopefully we'll have a lively discussion as we go along or towards the end. And then in the second half is just the fourth part here. I will talk a little bit more about the area of my research that some people already know, of course, the Lambda Calculus very well. But I will try to explain it also to those people who don't know it well. It's a particular case study, if you wish. Okay, so what was the trigger for these considerations? This is a talk and a paper by Eugene Paul Wigner, who was a Nobel Prize winning physicist, and in 1959 he gave this lecture called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. This paper that was written up after the talk is easily available on the internet, and I recommend that you download it and have a look at it. It's very readable, very curious piece of work. So, but what did he say about mathematics and physics? So he has a little story at the beginning. He says there is a story about two friends who were classmates in high school talking about their jobs. One of them became a statistician and was working on population trends. He showed a reprint to his former classmate. The reprint started as usual with the Gaussian distribution, and the statistician explained to his former classmate the meaning of the symbols for the actual population, for the average population, and so on. His classmate was a little bit incredulous and was not quite sure whether the statistician was pulling his leg. How can you know that, was his query. And what is this symbol here? Oh, said the statistician, this is pi. What is that? Why, it's the ratio of the circumference of the circle to its diameter. Well, now you're pushing your joke too far, said the classmate. Surely the population has nothing to do with the circumference of the circle. So you may know that in the density function of the Gaussian distribution, there is a factor of 1 over 2 pi in the formula, and the pi is the number that we know from geometry. It is the ratio of the circumference to the diameter of the circle. So this is the introductory story, but then Wigner has, I think, 3 or 4 examples where he explains more detail what he means. So one of his examples is the complex numbers. So the complex numbers, I think everybody here knows, can be written as a plus ib, where I is just a constant about which we know nothing else but that I squared equals -1. It was invented during the Renaissance in Italy, with Cardano and Bombelli. And for several centuries, people had no idea what that I could actually be. And I could say, you can ask a mathematician nowadays, and a mathematician would still not know what I is in an ontological sense. But from an abstract point of view, we know that these numbers here, they form a field, which means that we can add them, we can subtract them, multiply them, and if it's not 0, we can also do division. And the amazing theorem about the complex numbers is that every polynomial of degree n has n roots in the complex field. So if you're a mathematics student, then you learn that in the second year, I guess. And if you do a complex analysis, you also learn a proof of this theorem. It was first postulated by Carl Friedrich Gauss, but the proof wasn't quite correct, and I think it was Argon who had the first complete proof. But Gauss liked the problem so much that he published the same result 2 more times. So it's called the fundamental theorem of algebra. So very important about finding roots of polynomials. But Wigner says, she says, now look, when you look at quantum mechanics, which was discovered 300 years later, or postulated or studied, then that is modeled by self-adjoint operators on a Hilbert space over the complex numbers. And so he says, how could it be that a theory developed in the 16th century regarding polynomials have an impact or an importance in the description of the universe at the microscopic scale? How could that be? That was his question. And that's what he called the unreasonable effectiveness of mathematics. In fact, he could have used a much simpler example. Galileo, who was the first real physicist, he studied the laws of bodies as they fall. You can do this in school. Maybe somebody has done that experiment. Instead of having the body fall down, it falls down very fast. You let it slide along an incline, so it accelerates more slowly. And then you have a metronome, and every time the metronome ticks, you take a piece of chalk and you mark where your little ball is. And when you measure the distances, then the first distance after the first tick is 1 unit. After the second tick, it's 3 units. After the next tick, it's 5 units, 7 units, 9 units. How could it be that numbers which were invented for counting have such a strong link to the way the physical world works? So that is Wigner's question. But these ideas were not new. I mean, there's lots of other people who worry about, for example, Galileo himself said, philosophy, and I think he meant natural philosophy, is written in that great book which ever lies before our eyes. I mean the universe. But we cannot understand it if we do not first the language and grasp the symbols in which it is written. This book is written in the mathematical language, without whose help it is impossible to comprehend a single word of it, without which one wanders in vain through a dark labyrinth. And Kant said, in any special doctrine of nature, there can only be as much proper science as there is mathematics therein. And Einstein asked a very similar question to Wigner, actually. He said, how can it be that mathematics, being after all the product of human thought, which is independent of experience, is so admirably appropriate to the objects of reality? So everybody understands Wigner's problem. So in fact, Wigner ends his essay with you could say almost a religious statement in the last paragraph, where he expresses his profound awe at this fact that physics has a mathematical description. Okay, so this is very old. It was from 1959. It's many years ago. And people discussed Wigner's question, and people also made fun of it. So here is Mr. Gelfand from the Gelfand transform. Mathematicians know that. And he said, there's only one thing which is more unreasonable than the unreasonable effectiveness of mathematics in physics, and that is the unreasonable ineffectiveness of mathematics in biology. So, well, if the physical world is so mathematical, he said, everything maybe should be mathematical, but in his day, biology, he felt, had no mathematical laws underlying, and still biology, you could say, is just as important as physics. But actually Gelfand was certainly partly wrong, but it wasn't really discussed and discovered in his... Partly it was discussed. So here's a flower. This is very common in Europe. I don't know how common it is in Brazil. It's called a sunflower. Does it grow in this state? Probably not, but maybe further south. Huh? Does it grow? But it's maybe not more like a temperate climate plant. And here in the flower you have the seeds of the sunflower, and it looks kind of regular. If you are a little bit drunk, you see spirals or like a whirlpool pulling you down into it somehow. No? And so if you're so inclined, you might go and draw a little line to see this one arc here. See the arc? Yes? Now you can count how many arcs there are of this kind as you go around the flower, and I've done that. But you can count again. We're not going to count together. And if you count it this way around, it's 34 arcs. But if you look at it carefully, you see there's also an arc in the other way. Yes, you can also view that arc, and you go around the flower again, and you count that, and then you get 21 arcs that way. There's 21 and 34. Okay, so what? No? Maybe sunflowers in Brazil are different, but because it's the southern hemisphere. But no, it's not. No, it will always be 21 and 34 because it will be two Fibonacci numbers, two successive Fibonacci numbers. And again, the Fibonacci numbers go back to Fibonacci. Again, Italian Renaissance. I did this only to make Umberto happy. And we know now that there is no coincidence that you see the Fibonacci numbers in a growth pattern like this one. This can be explained, and it has to do with the ratio of two successive Fibonacci numbers approaching the golden ratio. And the golden ratio is that irrational number which is most difficult to approximate by a rational number, and that is why this occurs. So there is a simple chemical process which makes this happen. And so if you wish, this is just like Wigner. Why should the Fibonacci numbers, a very simple recursive definition, why should that appear in sunflowers? If you're interested, there's a nice book by Ian Stewart called The Mathematics of Life, and you might want to have a read. It's very nice. Okay, so now our question is, how is it with computer science? What's the relationship between mathematics and computer science? So that's what interests me in particular, and what I wanted to discuss in this lecture. Is it the same? Is it the same that mathematics is on the shelf and we just pull that mathematics out and we can use it in computation? Of course, we do this all the time, but is that how you can see it? And so in the next two sections here, I give a little, very, very short history of mathematics. I know it's kind of crazy, but to do this in one talk, but I'll try anyway. So when you go to the very earliest mathematical text that we have, that's called the Rhine Mathematical Papyrus, and it's about 3,600 years old. It's from Egypt, and people have deciphered it, what it says. It's a mathematical text. It is the oldest mathematical text that we have, or one of the oldest. And what is it about? It has some exciting formulas, like this one. It has linear equations and also has some geometric problems. And the one question, of course, is there's lots of these examples of fractions. So why were the Egyptians so interested in fractions? Why was so much interest in that? So here's a question for you. Any ideas why they were so interested in fractions? Geometry, I think we all learned that in school. They were interested in geometry because the Nile would flood the country, and after it receded, they had to again measure the country and see where everybody's field was. But why were they so interested in fractions? What do you think? Huh? Tax. I think so. Yeah, I agree. Must be tax. No? I totally agree with you. Of course, we don't know, no? But I think that must be the reason. No? And then we make a big jump to Europe. This is a German guy. He's called Adam Ries. And we still use it in the German language. We will say to small children, we will say 2 plus 2, according to Adam Ries, is 4. No? So it's like a little saying that we say, because Adam Ries in his time, this is the 16th and 17th century, he wrote very influential books, according to which many, many, many generations of people learned to calculate. So it was one of the first mathematical textbooks in Germany. And there's similar people in other countries, but that's the one that I know quite well. And this doesn't come out so well. It's a little circle here, not a circle, an ellipse. And so really, when you go to this early tradition, then mathematics and computation or calculation was really one and the same things. You go to Adam Ries's time in Germany, 16th century, and if somebody were to say, I'm a mathematician, then what they would have said is a Rechenmeister, which means a master of calculation. So really that was the role of mathematics, was to tell people how to calculate. And as you were saying, whatever was tax, Adam Ries had a job in the local mines, and he had to compute things about, how they bookkeeping and stuff like that. But there was another tradition, which is also very old, but by the time the 16th century in Germany, it was completely forgotten. And that started with the Greeks, as far as we know. But the Greeks themselves say they learned it from the Egyptians. So maybe the Egyptians did a little bit of mathematics as well. and maybe even the Indians and the Chinese, but we know very little about that. So people like Thales, Pythagoras, Euclid, of course, and Hypatia was a woman, one of the first female professors, or maybe the first female professor of mathematics that we know about, living in northern Egypt. And for them, of course, mathematics was not calculation, it was about proving logical statements. Whether that had an immediate application was not so important. It was about proving statements from axioms, deduction. And that's a completely different tradition. And of course now when you come to university, you learn about mathematics in the sense of the Greek tradition. And everybody hopes that by the time you come to university, you will have done that other tradition in school sufficiently well that you don't need to think very hard about 1 over 101 plus 1 over 101 and what all that might be. No? Okay. So I have a picture for that. But of course, you know, the need for computation was always increasing as well. So with the Enlightenment and the Industrial Revolution and the emergence of engineering and the physical sciences, all of a sudden computation or calculation was much more than it was, you know, to compute what you needed for bookkeeping or computing your tax. And it was so complicated that people wanted to have mechanical calculators. And I have a picture of one here. There's one called the Brunswiga. I have one at home. My father used it until the end of the last millennium, I guess, and then he gave it to me. It's not a computer, but it's a mechanical calculator. And then there's another guy here, Zuse. I don't have a picture of his machine, but he built a calculator in his father's living room in Berlin. And again, it was meant to calculate. And what did Mr. Zuse want to calculate? What do you think? It wasn't about tax returns. It was not about geometry. What did he want to calculate? So does anybody know that? Any mathematician has an idea what the first computers were used for, both in America and anywhere else? No. That was England, very specifically, the bomber and that. The war, and what did they want to do in the war? Why was Fourier, why did he become famous in France? Okay, so it was about solving ballistic, yes, solving differential equations to compute the ballistic curve to throw bombs on each other. So it was about the war, really. It was about the war effort, very much. And of course in America, the ENIAC, that was used to compute the calculations for building the atomic bomb, very much. Okay, so here's a picture of people using these mechanical calculators. No? And so I would say in this phase, mathematics was a much bigger thing, but calculation and computation was still an important part, but it was part of mathematics. It's just part of mathematics. It was applied mathematics, you could say. Okay, and so now we come to the next section here, and I think all this changed in 1937. Of course, it was a revolution in a way. In hindsight, you can say it was a revolution, but at the time, of course, people did not see it like that. With a paper by Alan Turing on computable numbers with an application to the Entscheidungsproblem. And in this, he argues why his model of computation or calculation is a sensible one, and we now call that the Turing Machine. And I guess as a computer science student, you've heard of the Turing Machine in theory of computation. And in this paper, he argues very carefully that a Turing machine can do everything that a very careful mathematical student could also do, or any calculator really. And he says the behavior of the computer at any moment, and he did not mean a computer like an Apple machine nowadays, he meant a person who computes. So when he says computer in 1937, he means a person. He says the behavior of the computer at any moment is determined by the symbols which he is observing and his state of mind at that moment. We may suppose that there is a bound to the number of symbols or squares which the computer can observe at one moment. If he wishes to observe more, he must use successive observations. And he goes on and tries to explain that all of that can faithfully be modeled by a Turing machine. Well, why was that so important? So let's see, why am I saying a new phase started with this paper? So the Entscheidungsproblem was posed by David Hilbert, very famous mathematician. We had the name before. And he posed this question not in his famous problems, but in a 2028 conference, and then published it in his book on theoretical logic. And his question was, is there a mechanical process by which we can decide any mathematical question? Well, nowadays perhaps that seems an absolutely crazy idea, and I suppose we wouldn't have a department of mathematics in any university if there was a positive answer to the Entscheidungsproblem. Because you don't need any mathematicians if every mathematical question can just be solved by a mechanical procedure. There's a mechanical procedure that you can use to solve a quadratic equation. You learn that in school. And then there's one for a cubic and a biquadratic equation, which nobody ever learns anymore. And then there's a method for linear equations and so on. And so his question was, maybe there is a procedure to solve any mathematical problem just by following a certain procedure. And Turing said, no. There is no such thing. And so I'm saying that is the moment when computer science started. So Turing said, computable functions have properties that limit what you can do by calculation. So it's not like the old calculation where you say, well, take any mathematical subject, more or less, and then approximately you can do this by calculation. Turing said there are things which you cannot do by calculation. That was the first theorem of computer science, which I hope everybody learns here as well. Theory of computation from you maybe, huh? Joao? You can ask. From Benjamin. Okay, yes. And so now computer science becomes, or computation becomes a subject that we can study in the same way as the physicists study the real world. So we as computer scientists, we can study computable functions because that is something. It is something real. That's what Turing says. It's not something that is kind of vague or unspecified. No, we'll come to that in a moment actually. It is something very precise because it's our natural world as computer scientists. We study this universe of computable functions just like the physicist starts the universe of the physical world, or the biologist studies the universe of living things. Okay. But let's just say this, no? That's what I just said. Okay, so now computation becomes, I say, has a flavor like a natural science. And I say here that it has been a lot of mathematics to study this. And of course we cannot try to quote everything. And sometimes we had some Wigner moments where the mathematics was already existing and we saw that it could be applied to computation. And sometimes we would have liked that, but the mathematics did not exist. And the mathematics had to be newly invented by computer scientists and mathematicians in order to understand this new phenomenon, computing or computable functions. And that process, you could say, is still going on. So you could say mathematics is a big subject, and it has relevance to many sciences. It has relevance to computation. But computation is no longer a subset of mathematics. It's something in itself. Everybody gets my thesis here. No? So that is a way of describing the state of affairs until, say, 5 years ago. So I might try to make a pitch that the thing has changed again, perhaps, in some ways. No? All right. Okay, so let's have a look at a case study. And let's see how this interplay between mathematics and computation shows itself in the Lambda Calculus. Is that okay? Everybody okay so far? Everybody wants to attack me or throw naranjas at me? Yes, I want to say that now. Yeah, okay, that's part of that story. Okay, it's a bit speculative, I guess. All right. Everybody okay with what we said? Yeah, so far? All right. So the Lambda Calculus came from a logician, but not a computer scientist, also in the 1930s. His name was Alonzo Church, very nice name. And what is it? I don't know whether you have seen that before or not. I know one person has definitely seen it before, a lot. For example, we write lambda x dot x squared. It's a very, 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 very condensed notation. But what it means is this is the argument of the function, the x, and this is the body of the function. And so it says, give me an x, I will compute x squared and give you the result back. No. Remember that from the Lambda Calculus lectures, Umberto? You remember that much, no? Okay, good. Just about. Okay. Oh, here's another example. It's something that in mathematics already we don't usually write down. This is, I say, you give me an x, and I give you back the function which is the exponential function to base x. No? So the Lambda Calculus is very flexible in returning a function, also accepting a function as an argument. In mathematics we usually have functions, not always, but usually we have functions from real numbers to real numbers, or maybe something like the integral from functions to real numbers. But in the Lambda Calculus you can very freely form what we call higher order functions. No? And so here the Lambda, so why did Church invent the Lambda Calculus? He wanted to give a foundation to mathematics based on the concept of a function rather than set. He thought it was more fundamental than the notion of a set. And he was hoping that he would be able to avoid Russell's paradox in that way, which was still a very hot topic in those days. We still had the foundational crisis of mathematics in full swing. And so he said, let's see what I can do with functions instead of sets and classes. And that didn't succeed. People very quickly pointed out some contradictions or paradoxes in the Lambda Calculus. But Church had the good sense to think about computability, which was the new show in town, following Turing's paper. And he showed that whatever Turing could compute on his machines, he could also compute in the Lambda Calculus. And Turing showed that everything you could do in the Lambda Calculus, he could do on his machine. And so then, with a few more translations like that, we then have the Church-Turing thesis, which says every function computable by some effective means is also programmable. So if you come up with some way of computation, then it might as well be done on a Turing machine. You might as well do it on your iPhone or whatever. They're all equivalent. They're all the same. There is no machine which is fundamentally, from a mathematical point of view, more powerful than any other machine. Okay, again, it's something. It's not a theorem. It's a thesis, but it's sort of computer science as a science, something that we might worry about, think about, study. And you could say that's a Wigner example, because Church's initial motivation was to give a foundation for mathematics, but then this new stuff came along, computer science, and lo and behold, you could use it and do something very fancy with it in computer science. So maybe it was just like Wigner, it was invented for something else, and then it was useful in computer science. Well, I want to argue on the next few slides, you could also have a much more critical view of the Lambda Calculus as it was invented by Church and as it was studied by the mathematicians initially. Because when you look at this thing that takes an x and gives you the exponential function, then surely, I should know what that x is. For example, as far as I know, it should better be a positive real number. So I could annotate a type here and say x should be a positive real number, and then the y can be any arbitrary real number, and then this x to the y makes sense. Otherwise, I get a much more complicated theory, as you perhaps know. And so you could use type annotations to make more precise what you mean by that. But then you discover that this typed calculus, we call it the typed Lambda Calculus, is very restricted, and it is not a Turing-complete calculus. So the untyped calculus is kind of crazy, but the typed calculus is not Turing-complete. So it is too weak. So that's what Church had defined, and neither the untyped nor the typed is actually good for computer science. So that's what I'm saying here. I'm jumping ahead here. So the untyped calculus is expressive but contains a lot of junk. The typed calculus is very nice, very easy to understand, but it's limited, it's not Turing complete. And anyway, the mathematicians completely ignored it. You know, they said, what's that? It's rubbish. So the first calculus after the war, well, the first conference on the Lambda Calculus, Eleni, do you know when it was? Well, it was in Holland in the 60s. And who were the attendants? There were 3 attendants at that conference. It's a very small workshop. So it's more here than that. It was Henk Barendrecht, Roger Hindley. Huh? Yeah. Okay, so 3 people, and they met in Henk Barendrecht's house, which was a windmill in Holland, and that was the first conference. The second conference, I think, was organized by Roger Hindley in England, and it was a big success over Holland. It had 5 participants. And the third workshop was 2 years later, was in Darmstadt in Germany. That's where I am coming from originally. That's where I did my PhD. And the numbers had exploded. I think there were 12 members already. And there's a nice story to that, which I can't tell you, but that was the early 70s, were the wild years in Germany. And they were all very nearly arrested because the police thought they were all drug addicts. But they, in the last moment, realized they did look a bit strange, but that strangeness did not come from drugs. It came from something else which they didn't understand. So it was the Lambda Calculus which made them so different. And then the next conference was in Italy, was organized by Corrado Böhm in Rome, and it had more than 100 participants. And ever since then, the Lambda Calculus, because of computer science, that what happened, the computer scientists and the mathematicians or the logicians got together, and they saw that they could do a lot together. And then, as a field, it has exploded. And there's a lot of people working in the Lambda Calculus in the intervening years. Okay, I'll say this here. Well, in computer science, the Lambda Calculus was introduced by John McCarthy. He was educated in Princeton. He was a student not of church, but in those days, as a PhD student, you would talk to other PhD students and say, what are you doing? What are you doing? And, you know, I'm doing this, I'm doing that. And he learned about the Lambda Calculus, but his PhD was on something completely different. But later on, he became involved in artificial intelligence, and he defined this language Lisp, that I think many computer scientists have heard of. And when we in mathematics would write lambda x, lambda y, x to the y, in Lisp you would write lambda x, lambda y, x, xy. So you write almost exactly the same. And John McCarthy was not just the inventor of Lisp, he also was a member of the ALGOL committee, and he introduced some lambda notation, or notation that's very similar to lambda, to the ALGOL family. And then the youngest members of that are C, C++, and Java, and those languages. So the Lambda Calculus was quite influential there. No? Okay, so let's explain a little bit. We said the Lambda Calculus doesn't match, and one thing is the untyped calculus has a lot of junk, I said. And so Dana Scott in 1969, he looked at that for the first time. He was a logician. He was visiting Oxford. He looked at that and he said, well, it's a terrible calculus. I can't make any sense of that. And he suggested an alternative, which is a typed calculus. But quickly afterwards, he discovered that you could make a model for the untyped calculus where every lambda term denotes a function on what we call a domain. So actually what I've called junk earlier can be quite precise in Dana Scott's domain theory. And again, you see that the mathematicians, they looked at the lambda calculus, they had it, but then they said, well, it's no good. And they ignored it apart from a handful of people. And so you cannot say that McCarthy or Dana Scott or people in Oxford at the time, that they took the lambda calculus off the shelf and it was the right mathematical theory to use in computation. That was not the case. So you cannot say that's an example like Wigner's. But the Lambda Calculus as a mathematical subject only became a fruitful mathematical subject because the computer scientists became interested. And so Dana Scott started the subject domain theory, which is where I spent most of my life in. And what are they? For those who are mathematicians, they are sets which carry an order. And again, people started to study that, and they discovered there was some link to topological algebra, but again, it was only a partial connection, and a lot of mathematics had to be newly created. Although there had been something like 70 years of topology, the topology that's important in domain theory was new, had to be newly discovered, non-Hausdorff topologies, and it's not that the mathematicians had done that already. No. Okay. So I don't think it is at all a Wigner example. No? So I'm jumping ahead a little bit, but that's okay, I guess. So Dana Scott, we said, so the untyped calculus is maybe too undisciplined, although we can make some sense of it. The typed calculus is very meager. And so Dana Scott's suggestion in 1969 was, but if you extend, the work by Giuseppe Peano and other people in recursive function theory, you add the integers, you add successor and maybe predecessor, but it's not necessary, a test for 0, if then else, and a recursion operator, then in fact you get a language which is Turing complete. It's called PCF, it's a theoretical language, but it is just as powerful as a modern functional language like Haskell or ML or any other, or F#. And you would say, aha, so now we have the answer. So we study PCF, and let's use all the mathematics that we know and study this language. PCF is a very mathematical language. So hopefully the mathematics will tell us something about it. That was done by Gordon Plotkin in a landmark paper in 1977. And he said, it's a very nice language. It's exactly like Haskell, say. But according to the mathematical model, something in the language is missing. And he put his finger on that, and he defined some new constants called parallel OR and parallel conditional. But nobody ever wants to add that to Haskell or functional language. Or otherwise, he said, this model that Scott built, the mathematics, is somehow not quite right. It has to be adjusted. No? So there's a mismatch between the programming language and the mathematical model. So unlike Wigner, for Wigner, the complex numbers, he says they're exactly what you want for quantum physics. In computation, we have this domain model. It is very, very beautiful, but it does not fit exactly the computational language. So it is very, very different, no? In some sense. So some shocking discoveries. Well, maybe you're too tired to be shocked now, but I'll try to shock you into action. No? So as I said, PCF, Gordon Plotkin discovered, should be extended to make a match with the math, but nobody did that. The mathematics, can you adjust the mathematics? Well, Ralph Loader in 2001 showed a theorem which is very difficult to prove, not so difficult to explain, but difficult to prove. He said, well, actually you cannot adjust the domain model. It's impossible. There isn't a mathematical model out there that, is sensible in the sense of actually being a model of the language and fitting computation precisely. So there is a mismatch between language and model, and it cannot be argued away. But the PCF, or Lambda Calculus, allows higher order computation. And for example, there's also no Church-Turing thesis for higher order computability. So there are genuinely different ways of computing at higher types. Again, it's very disturbing. At the numbers, we have the Church-Turing thesis. So there is a lot going on here that, from a mathematical point of view, is very disturbing. Okay, the full abstraction problem, which is what we're talking about here. You may have heard of game semantics. And that is a different approach, which did not exist. It was invented by computer scientists to solve this problem. So it was not already pre-existing mathematics, as Wigner was postulating. It was mathematics that computer scientists created. Yeah, but it gets worse. That is how harmless. It gets even worse. So you look at polymorphic functions. So you look at the lambda term, lambda x dot x is a very simple function. You give me something, I'll give it back to you. No? If you're a nice guy, I guess. No? I'll give something, I'll give it back. No? So it's the identity function. And what is its type? Well, it could be any type. It could be money to money, or it could be pebbles to pebbles. It can be anything you want. It can be functions to functions. And so that was the idea of polymorphism, which was first proposed by Strachey in Oxford in 1967. And the fact is that mathematics, as we know it, as we learned it, is completely at odds with the idea of polymorphism. John Reynolds wrote a famous paper in 1984 where he said polymorphism is not set theoretic. There is no set theoretic model of the polymorphic lambda calculus, yet it is very, very easy from a computer science perspective to understand. And then Andy Pitts wrote a reply 3 years later where he said polymorphism is set theoretic constructively. So if you think about sets constructively as a constructive set theory, then you can also build a model of the polymorphic lambda calculus. Oh, what's going on here? No? Okay. All right. So what's the message here? I would say there are parts of computer science that are very non-Wigner. So the Wigner idea was that mathematics is this absolute thing out there. It's beautiful, and I think it's very beautiful. And as a physicist, you just pick apart and say, yeah, that's how I use it to describe some natural phenomenon. And if I cannot use math to describe this natural phenomenon, then maybe it doesn't even exist. So all this stuff about combining gravity with quantum physics, it has to have a mathematical answer, right? That's what they're looking for. They haven't found it yet, but there's a strong belief that if there's an answer, it will be a mathematical answer. Maybe a string theory, dimension 12 or whatever. No? But physicists cannot think in any other way. But in computer science, you look at the history of computer science, it's just one example. And what we discover is that mathematics is beautiful, but there are many, many instances where it does not fit computation. Okay. All right, so, maybe you don't care about that. It's anyway getting late now. Okay. Okay. So you could say, well, never mind all this trouble. It's certainly a very interesting topic because we have this language PCF and type theory. And so, for example, you get these languages of Camel and Haskell, which people use and love very much. And I talked to you about polymorphism and this constructive model that you have for that in constructive set theory. And so there is a renewed interest in the foundations of mathematics as a result of looking for a link between mathematics and computer science. So just to explain to you what that is, it's called the Curry-Howard isomorphism, which is a very hot topic right now again, which says proofs are the same as programs and propositions in mathematics are the same as types. No? And so what do you mean by that? So for example, you learn in logic modus ponens. Is that okay? Is that a logic in your sense? No? If you have modus ponens Umberto, can you accept that? No? Okay, and then a computer scientist says, I've seen that. If I have a function from A to B and I apply an argument from type A, then f of x will be of type B. So that's modus ponens in computer science, and this is modus ponens in logic. And if you remove the x colon stuff here, then you get this on the left-hand side exactly. This is called the Curry-Howard isomorphism. There has been a lot of work on that. So originally it was just, as I said, for propositional logic and the simply type lambda calculus. And it's fairly easy to establish. A lot of people have worked on it and extended it to much stronger logics. and more expressive programming languages, but not the kind of logic that you use in mathematics. And that has led to a mathematical foundational theory that you see Church was trying to do, but he couldn't. And it's known as Martin-Löf type theory. And to proof assistance, Coq and ACTA. So the idea of ACTA is, in this proof assistant, you write a proof in mathematical language, in this intuitionistic type theory, and then you press a button and you get a program out of that. Because a proof is at the same time a program. There is this very strong isomorphism. I said, well, that's a very, very nice way of programming. Maybe instead of writing these long computer programs full of bugs, instead what I do is I prove a theorem. I have a proof assistant which will tell me whether the proof is correct or not. And then at the end, my program just falls out by the Curry-Howard isomorphism. And that is a very hot topic because ACTA is still under very active development. I think Coq as well. No? And so 2 years ago, I think there was a group of very intelligent people meeting at the Advanced Institute in Princeton. I'm not one of them, by the way, but on homotopy type theory and the univalent foundations of mathematics. There's not much I can say about that now, because we're running out of time. They wrote a book which you find on the internet for free, homotopy type theory. So the story there is that this Fields Medal winner, Voevodsky, discovered a mistake in a proof that he had published 20 years earlier. And he said, well, why did it take 20 years to discover that mistake? Obviously, my field has become so complicated that even the referees cannot check my paper anymore. And he was looking for a proof assistant, and he was discarding all automatic theorem provers until he came to Martin-Löf type theory, and then he became very interested, not because he thought that was the answer, but because that was the only proof system that he didn't understand. And so he said, maybe I should really study this a bit more. And he suggested some additional type theory from his intuitions into homotopy, because he was a homotopy theorist. So that's Voevodsky here. This is Steve Audi, one of the co-inventors. So now there's a link between algebraic topology and computer science, which is very, very fascinating. And you could say, it's another Wigner moment. No, it's not. It's not, because the mathematics is changing as we try to understand computation. And so the future of mathematics could look very different from what we have seen in the last, say, 3,000 years. So this is the last phase that I was promising. Maybe in the future, when you write a mathematical paper, you will not write the proof, but you will supply an ACTA program, a file of ACTA code, and then you just run the ACTA proof checker, and you don't do any refereeing. The proof checker tells you this proof is correct or not. No? And of course, once you have a proof checker, you can do experimental mathematics. You can sit down on your computer and you could say, well, suppose I had a logic where the powers of 2 were the designated element, something crazy, something totally crazy, and just play around, and the proof checker says, no, it doesn't work, no, it doesn't work. Maybe I'll take the prime numbers, no, it doesn't work. No. And then maybe something else. The perfect squares, yes, the proof checker says, now you can prove your stuff. No, say, okay, write a paper, here's the ACTA code, fantastic, next one, your next paper. No? But maybe we will have different mathematics, because maybe Umberto will be using ACTA and I use Coq, and what he proves in ACTA cannot be shown in Coq, and what I show in Coq he cannot show in ACTA. So it's a very strange idea what mathematics might be, no? Okay. And so perhaps the future will be, again, a complete unity of mathematics and computation again. So maybe the mathematician will say, actually, mathematics and set theory, that was kind of a Platonic invention, that you could have infinite sets and sets which have higher infinities, the uncountable and higher infinities. That was just crazy inventions. But computer science, computing functions, that's real, because we can run them, right? That's real. So maybe mathematics, that's really where mathematics should be. It should be based on something real, not based on some kind of Platonic universe. And so maybe mathematics will change completely. I don't think it will happen, but it's just a nice thought. No? Okay, so here are some of the sources that I use, but I mean you can find those by just Googling these things very quickly. And so I'll leave you with those thoughts. Thank you very much for your attention.